This is Goddess of Science Physics, and we're going to start talking about momentum today. This is part one of the momentum series, aptly named Momentum. Okay, so what is momentum? A lot of times you've probably said the word momentum. Oh, they're doing well. They got a lot of momentum going. You hear that a lot with sports teams and things like that. But what really is momentum? In the science sense, momentum is the inertia in motion. So back in chapter 5, 4, it was, when we were talking about inertia, we said that an object at rest will stay at rest. That's not momentum. But an object in motion will stay in motion. That is the momentum part of that law. Okay, so in one of the things that you probably have seen is one of these little Newton cradle things, and when you pull one of the balls out, it falls back down, swings back down, hits the next one, and then the momentum actually travels all the way through, and then the very last ball will swing out. And that's an example of the momentum being conserved. Okay, so the main idea of section 7.1 is moving object can have a large momentum if it has a large mass, a high speed, or it could be both. So that's kind of what we're going to talk about in this very first section. So remember, you don't have to write down the red stuff. It's harder to stop a large truck than a small car when both are moving at the same speed. So, which kind of makes sense. If you have this giant 18-wheel truck, it has a great big huge mass, and even if it's going at a relatively low rate of speed, it's still going to be really, really hard to stop that. By the same token, if you have a little tiny Mini Cooper which doesn't have nearly as much mass, but if it's going at a very high rate of speed, again, it's going to be difficult to stop that. So the truck has more momentum, which is inertia in motion, than the car does. Okay. So factors that affect the momentum, as we just kind of talked about, one of them obviously is the mass. It's really much harder to stop something that's really large. If you got two things going at the same speed and one is like really, really huge and the other one is really, really tiny, it's easier to stop the thing, if they go in the same speed, that is smaller than larger. So mass is definitely one of the factors that affect momentum. The other factor that affects the momentum is the velocity, how fast the object is going. If you have two cars that have exactly the same mass and one of them is going twice the speed, it's going to be twice as hard to stop that car. It wants to keep going. Law of inertia says that an object in motion wants to stay in motion. And you probably have experienced this if you've ever been traveling down, say, Madison Avenue, and suddenly somebody pulls out in front of you or whatnot, and the driver has to put on the brakes. What happens to you? You kind of move forward toward the windshield, toward the front of the car, because you want to keep going. That's why we have seat belts. So if you're riding your bike and it has front and rear brakes, if you just squeeze the front brakes, you're probably going to keep going and go over the handlebars, which is not fun for anyone. So two factors that affect it are mass and velocity, and we have a new formula here. Momentum equals mass times velocity, which kind of makes sense because those are the two factors that affect it. Now, this chapter is the chapter of very weird letters to represent our quantities. Most people would think momentum, oh, we'll use an M. Oh, sorry, we can't use an M, lowercase m, because lowercase m is mass. Well, let's use an uppercase M. Oh, sorry, you can't do that, because in chemistry, an uppercase M is molarity. Oh, so we got to think of another letter to use. Well, I guess, logically on the part of whoever put this together, momentum is actually a lowercase p. Now, you can't use an uppercase p because remember last chapter we talked about the uppercase p being pressure. So this is lowercase p equals lowercase m times lowercase v. So this is a new formula that we're going to be using a lot. So the units are not only is this the chapter of the weird letters representing quantities, but it's also the chapter of very, very weird units. So the unit for momentum is kilograms meters per second. Kind of a weird thing. And no, there's no shortened way, like meter, newtons per meter squared was a Pascal. There's none of that business. It's just kilograms meters per second. Okay, so a moving truck has more momentum than a car that's moving at equal speed because the truck has a greater mass. Okay, so if they're at equal speed, the mass determines which one has more momentum. If they're going at the same speed, then if they have the same mass, then whichever one is going faster determines which one has momentum. So a fast car can have a lot more momentum than a slow truck. So we were talking about which one has greater momentum. If you have an 18-wheeler that's sitting in the parking lot of Walmart, is it going to have more momentum or less momentum than a turtle that is walking down the sidewalk? Think about that for a minute. Okay, you're done thinking. The turtle, even though it's smaller and is moving very, very slowly, obviously has more momentum because the 18-wheeler sitting in Walmart's parking lot has no momentum because it's not moving. So anything can have more momentum than something that's stopped. A mosquito that's flying can have more momentum than that 18-wheeler that's just stopped somewhere. So you might want to keep that in mind. Anything at rest has no momentum at all because it has no velocity. Well, how about that? Okay, truck rolling downhill has more momentum than a roller skate at the same speed because the truck has more mass. Same speed, whichever one has more mass, that's more momentum. And there's our roller skate, which is a real old-fashioned roller skate, and there's our truck. If the truck is at rest and the roller skate is moving at all, the skate will have more momentum. So if one of them has zero velocity, then obviously the other one is going to have momentum because it doesn't matter what the mass is times zero, the momentum is going to be zero. Okay, so that's it for this time. Thanks for joining me. Have a great day.